the area function. Okay, so let's begin with slide 1, titled the area function. In the study of calculus, we often encounter the definite integral as a way to find the total area under a curve between two fixed points. Now, you've likely already learned about definite integrals. They give us the area bounded by a curve, the x-axis, and two vertical lines. Think of it as slicing up the area into infinitely thin rectangles and adding them up. Importantly, with the definite integral, those boundaries, the starting and ending x values, are fixed numbers. To understand the deeper connection between differentiation and integration, we must introduce the concept of the area function. This is where things get a little more dynamic. We're going to build on what you already know about definite integrals, but instead of just calculating a single area, we're going to create a function that represents the area. This is crucial because it highlights the inverse relationship between integration and differentiation, something we'll explore further as we move along. Instead of looking at the area between two constant numbers, the area function treats the upper limit of integration as a variable. This is the key idea. Remember how in a definite integral, we have a lower limit and an upper limit? Well, instead of the upper limit being a specific number, we're going to let it be a variable, usually denoted as x. This means the area we're calculating isn't fixed. It changes as x changes. This allows us to observe how the area changes as we move along the $x axis. Exactly. By making the upper limit a variable, we can see how the accumulated area grows or shrinks as we move the boundary along the x-axis. This dynamic perspective is what the area function gives us, and it's a powerful tool for understanding calculus. In the next slide, we'll visualize this concept with a curve and a sliding boundary, so you can really get a feel for how it works. Conceptual understanding. Okay, so let's move on to slide 2, where we're going to build a conceptual understanding of what this area function actually is. Now, remember from the previous slide, we talked about definite integrals giving us the area under a curve between two fixed points. We're now going to take that idea a step further. First, imagine a curve. We can represent this curve with an equation, and we'll call it y equals f of x. Think of f of x as just some function that describes the shape of the curve. Now, let's say we want to calculate the area of the region that's bounded, meaning enclosed, by this curve, the x-axis, and two vertical lines. Here's where it gets interesting. One of these vertical lines is fixed. We'll call its x-coordinate a, so it's a constant, a starting point. But the other vertical line isn't fixed at all. It's what we call a sliding boundary. Its position is defined by x, so as x changes, this line moves along the x-axis. As we slide this boundary to the right or to the left, think about what happens to the area trapped under the curve. It changes, right? It gets bigger or smaller depending on how far we move the line. That changing area is exactly what the area function captures. We denote this area function with a of x. A of x is essentially a mathematical rule, a formula that tells us the exact area of that region, the area under the curve bounded by the x-axis, the fixed line at x equals a, and the sliding line at x, for any value of x within a specific interval. We usually denote that interval as a to b, meaning x can take on values between a and b. So, a of x isn't just a number, it's a function itself. It takes a value of x as input and gives you the corresponding area as output. This is a crucial concept, and we'll see how it connects to the definite integral in the next slide. Mathematical definition. Okay, so let's solidify our understanding of the area function with a formal definition. As we discussed on the previous slides, we're moving beyond just calculating the area between two fixed points, and instead looking at how the area changes as one of those boundaries moves. This slide presents the mathematical expression that captures this idea. We define the area function, which we're calling a of x, as the definite integral from a to x of f of t dt. Let me break that down piece by piece. First, a of x represents the function that will ultimately give us the accumulated area for any given value of x. Think of it as a rule that takes an x value as input and outputs the corresponding area. Next, we have a, This is our fixed lower limit of integration. Remember from our earlier discussion, this is the starting point, the x value where we begin accumulating area. It remains constant throughout. Now, x is the crucial part. This is the variable upper limit. As we change the value of x, we're essentially sliding the right-hand boundary of the area we're calculating. This is what makes it an area function rather than just a single area value. Inside the integral, we have f of t. This is the integrand, the function that defines the curve whose area we're finding. Now pay close attention here. We're using t instead of x inside the integral. This is really important. T is what we use as a dummy variable. It's just a placeholder for the variable of integration. We use t because x is already taken as the upper limit of integration. If we used x inside the integral and as the upper limit, it would create confusion and ambiguity. Finally, dt simply indicates that we are integrating with respect to the variable t. It tells us that we're summing up infinitely thin rectangles with width dt and height f of t to find the area. So, putting it all together, this formula, a of x equals the integral from a to x of f of t dt, gives us a powerful tool to analyze how the area under a curve changes as we move along the x-axis. In the next slide, we'll see a real-world example of how this concept applies to distance and velocity, which will help to further cement your understanding. Real-world example, distance and velocity. This slide connects the area function to physics, specifically the relationship between velocity and distance. Think about it. If you know how fast something is going at every moment in time, how can you figure out how far it's traveled? Let's consider a scenario. Imagine a car is moving, but its speed isn't constant. It's speeding up, slowing down, maybe even stopping at traffic lights. We can represent the car's changing velocity as a function of time, which we'll call v of t. Remember, vt means the velocity at a specific time t. Now, if we want to calculate the total distance the car has traveled from a starting time of 0 up to some later time, which we'll call x, that's where the area function comes in. Let's break down how to apply it step by step. First, visualize a graph. We'll plot time t on the horizontal axis. That's our x-axis, and the car's velocity vt on the vertical axis, that's our y-axis. Next, we establish our starting point. Let's say the car starts at time equals 0. This is our fixed lower limit, just like in the area function we defined earlier. Then we have the current time, which we're calling x. This is our variable upper limit. As x changes, we're looking at the distance traveled up to that specific time. Now here's the crucial connection. The total distance traveled, which we'll denote as sub x, is represented by the area under the velocity curve from our starting time of 0 up to the current time x. Mathematically, we express this as the definite integral from 0 to x of v of t dt. Let me break that down. Sub x represents the distance traveled as a function of time x. The integral symbol, followed by the limits of integration, 0 to x, tells us we're finding the area under the curve v of t between those two time points. And dt simply indicates that we are integrating with respect to the variable t, representing an infinitesimally small change in time. Finally, let's interpret what this means. As time passes, as x increases, the area under the velocity curve grows. This increasing area directly corresponds to the total distance the car has accumulated. So, the area function in this case is a function that dynamically calculates the distance traveled as time progresses. This example will be helpful as we move forward, because in the next slide, we'll work through a specific mathematical example to calculate an area function. Remember, the core idea is that the area function gives us a way to accumulate quantities represented by the integral, and this has applications in many different fields, not just mathematics. Okay, let's move on to a real-world example to solidify our understanding of the area function. As we discussed in the previous slides, the area function essentially accumulates area under a curve. Now, we'll see how this concept manifests in a practical scenario. Mathematical example, calculating $x. First, let's state the problem. We want to find the area function for a simple linear function. Here's what we're given. Our function is f of x equals 2x. The fixed starting point, is 1. And our variable ending point is x, just as we've been defining it. Now, let's move on to the step-by-step calculation. Step 1, set up the integral. Remember, the area function a of x is defined as the definite integral from our fixed point to our variable point x of our function. So, we write a of x equals the integral from 1 to x of 2t dt. Notice I used inside the integral instead of x. This is crucial. We discussed this on the previous slide. We need a dummy variable to avoid confusion when x is also our upper limit of integration. So, we're integrating with respect to t, not x within the integral itself. Step 2, find the antiderivative. Now we need to find the antiderivative of 2t. The antiderivative of 2t is t squared. So, our area function now becomes a of x equals t squared, evaluated from 1 to x. The square brackets with the limits of integration indicate that we'll be evaluating the antiderivative at those limits. Step 3, apply the limits of integration. This is where we substitute the upper and lower limits into our antiderivative. We take the antiderivative evaluated at the upper limit, x, and subtract the antiderivative evaluated at the lower limit, 1. This gives us a of x equals x squared minus 1 squared. Step 4, simplify the expression. Finally, we simplify. 1 squared is just 1, so a of x equals x squared minus 1. Conclusion, and there we have it. For any value of x, the area under the curve y equals 2x, from 1 to x, is given by the formula x squared minus 1. This means if you plug in any value for x, you'll get the area trapped between the line y equals 2x, the x-axis, and the vertical lines x equals 1 and x equals whatever value you chose for x. Okay, so now we're going to put everything we've learned about the area function into practice. We'll work through a concrete example to really solidify your understanding. As we discussed earlier, remember the area function allows us to see how the area under a curve changes as we move the upper limit of integration. This is a great example of how the area function transforms a static area calculation into a dynamic function that depends on the value of x in the next slide. We'll look at some common mistakes students make when working with area functions, so pay close attention. Common mistakes to avoid. Firstly, it talks about confusing the variable of integration. Now, remember when we define the area function, a x dollar, as the integral from a to x of f t dollar dt? A very common mistake beginners make is writing the integral as the integral from a to x of f x dollar dx. Let me explain why this is incorrect. The variable we integrate with respect to, the one after the a, needs to be different from the variable we're using as the upper limit of integration. Think of it this way. X is acting as our ending point, telling us how far to integrate. We can't simultaneously use x to define how far we integrate and as the variable we're integrating with respect to. That creates ambiguity. That's why we use a dummy variable, like t or u, inside the integral. It's just a placeholder that allows us to perform the integration correctly without confusing the limits. Next, we have ignoring the sign of the area. This is crucial. Remember that the definite integral calculates what we call net area. What does that mean? Well, if the curve of the function f x dollar goes below the x-axis, the area in that region is considered negative. The integral doesn't just give you the geometric area, it gives you the area above the x-axis minus the area below the x-axis. So, you need to be mindful of the sign when interpreting the result of the area function. It's not always a simple positive value representing physical area. Finally, the slide warns against treating x as a constant. This is a subtle but important point. In the area function, a x dollar, x is the independent variable. This means x can change, and as x changes, the area under the curve changes. Therefore, a x dollar must be a function of x, meaning it outputs a different value for every input x. It's not a single number, it's a rule that tells you the area for any given value of x. Don't fall into the trap of thinking x is a fixed value. It's what drives the change in the area. Okay, let's move on to slide 6. This slide highlights some common pitfalls students encounter when working with area functions, and it's good to be aware of these before they trip you up. Okay, so keep these 3 points in mind as you practice. They're common errors, but easily avoided with a little careful thought. Now, let's move on to the final slide where we'll summarize everything we've learned. Key takeaways. The first point here states that the area function, which we denote as a of x, represents the accumulated area under a curve. Remember, we're not just finding the area between two fixed points anymore. We're looking at the area starting from a fixed point, which we called a, and extending up to a point x that can change. So, as x moves along the x-axis, the area under the curve changes, and of x tells us exactly what that area is at any given x value. Next, we have the mathematical expression for this. A of x equals the definite integral from a to x of f of t dt. Let's break that down. We've already seen this integral notation. It means we're summing up infinitely small rectangles under the curve of the function f of t with respect to t from the lower limit up to the upper limit x. Remember, we used inside the integral. That's our dummy variable to avoid confusion with the x that's acting as our variable upper limit. And dt simply tells us we are integrating with respect to t. Now, this is a crucial idea. The area function transforms a static area calculation into a dynamic function. Before, if I asked you to find the area between two specific x values, you'd get a single number. But now, because x is variable, a of x itself is a function. You plug in a value for x, and the function returns the area up to that point. It's no longer a fixed quantity, it's a relationship. Finally, the variable x in the upper limit determines the width of the region we're measuring. Think of it like this. As you increase x, you're extending the right boundary of the area, making the region wider. And because the width is changing, the total area, a of x, is also changing. That's why it's a function. It responds to changes in the input x. Okay, let's recap everything we've learned about the area function with this final slide. So, with this understanding, you've now grasped the core concept of the area function and how it connects to the definite integral. This is a foundational idea that will become incredibly important as we move forward into more advanced topics in calculus, like the Fundamental Theorem of Calculus, where we'll see how differentiation and integration are intimately related.